This is very similar to what I mentioned earlier about when we were verifying, is this a function, a solution to the differential equation? So consider dy dx equals k times y. So in our previous calculation, this is what we were calling f of y, right? So basically, if we flip dy dx, if we now consider dx dy, then the right-hand side is 1 over f, so it would be 1 over k times y. The denominator being k multiplied by y. So this implies that we would take the integral operator, right, both sides with respect to y. The left-hand side becomes x. This is x of y. Here you can argue this is 1 over k times natural log of y plus some constant. The derivative of the absolute value, derivative of absolute value of y is 1 over y. When you're doing this backwards, you have to write the absolute value there. Okay? If you're just thinking natural log of something, what's the derivative of that? Say 1 over that argument. But just remember to write the absolute value. This is just okay. So then this gives us an expression. So here, in other words, here we have x. Let me continue this. So we have x x is 1 over k times natural log of y plus some constant c. Okay? But what we need to do now is solve for y. Because we started with a differential equation of y. So what we want is the solution to this differential equation. We're looking for some expression y, some function y, which is a function of x. Okay? So even though we're doing this technique of kind of flipping the derivative and like flipping both sides of the equation for convenience, it's certainly easier to compute the integral of 1 over k times y, right? Then that's kind of what this technique is kind of exploiting. If you flip the expression, then you could solve for x in terms of y and then solve for y. Solve the differential equation and then solve algebraically for y in terms of x, which is what we do next. So if we're solving algebraically for y, here we have x minus c. X minus c equals 1 over k natural log absolute value. K times x minus c is natural log of this. And then if we exponentiate in both sides, we have e to the k times x minus c equals absolute value of y. So the thing is that this expression here on the left-hand side, we could think of this left-hand side because of properties of exponential. That left-hand side looks like e to the kx. That's my alarm. E to the kx times e to the k, e to the negative kc. That's simply applying the rules of exponentials, and this is still equal to the absolute value of y. So we could think of this exponential of e to the minus kc, we could think of that as a whole quantity, right? We could write that as d, okay? And this is e to the kx times some constant d, this is the absolute value of y.